Hi and welcome. This is the first video of a playlist about the preparation of alkynes, that is, compounds with a carbon-carbon triple bond. On the first 20 slides or so of this video, I'll show you some general properties of alkynes and examples of their uses, followed by examples of their preparation by elimination reactions. The next 4 videos are about CC bond forming reactions of terminal alkynes, that is, alkynes with one carbon-hydrogen bond. In part 6, I show you examples of alkyne preparations by isomerization and metathesis, and the last video is about the generation and synthetic uses of 6-membered cyclic alkynes. These are highly reactive and cannot usually be isolated, but are valuable synthetic intermediates. CC triple bonds consist of one sigma bond from 2 sp orbitals and 2 pi bonds from 4 p orbitals. Because sp orbitals have more s character than sp2 or sp3 orbitals, alkynes are more electrophilic than alkenes and tend to react more readily with nucleophiles and less readily with electrophiles. Deprotonation of terminal or internal alkynes is also easier than that of olefins. Phenylacetylene, for instance, has a pKa of 29 in DMSO, similar to aliphatic alcohols. The acidifying effect of alkynyl groups shows up when comparing the acidity of this group of phenylsulfones. A phenylethynyl group increases the acidity by 5 orders of magnitude more than a phenyl group. Deprotonated terminal alkynes are isoelectronic with cyanide, isonitriles, and with carbon monoxide. Thus, upon deprotonation, terminal alkynes can form strong, short bonds with a number of transition metals, in particular with copper 1 or 2, but also with other metals. In the presence of such metals, the acidity of terminal alkynes is enhanced, and deprotonation and complexation can already occur in pyridine or aqueous ammonia. For instance, if acetylene is bubbled through an aqueous solution of a copper 1 ammonia complex, copper 1 acetylide precipitates. Unlike calcium carbide, copper acetylide is unstable and explodes when heated to about 130 degrees Celsius. No gases, but only carbon and copper are formed during this thermal decomposition. The reason for this lack of stability could be that copper 1 is a stronger oxidant than the calcium dication, and thus capable of oxidizing the acetylide dianion to a radical. Silver acetylide is also highly explosive. In ionic acetylides, the typical distance between the metallic cation and anionic carbon is between 2.2 and 2.6 angstrom. In calcium carbide, this distance is 2.57 angstrom, while in the complex shown here, the calcium-carbon distance is 2.52 angstrom. Pure copper acetylide is amorphous, but with additional ligands, crystalline copper acetylides can be obtained. In most of these, copper is bound both to the terminal anionic carbon atom and to the pi bonds, as are sketched here. The copper-carbon bonds are shorter than in ionic acetylides, typically less than 2 angstrom. Copper 1 even forms complexes with internal alkynes, as those sketched here, again with rather short copper-carbon bonds. Particularly stable are also the complexes of alkynes with cobalt-0 carbonyls, which can even be chromatographed without decomposition. Few alkynes are commercially relevant, but a handful are prepared on a large scale. Before the emergence of the petrochemical industry, acetylene was a key starting material for many products, but has been largely replaced by ethylene. Some products that are still manufactured today from acetylene include the corrosion inhibitor propargyl alcohol, 1,4-butenediol, and 2-methylbutenol. The latter are mainly used for the preparation of vitamins. Alkynes can also be found in nature, mostly as defensive poisons in plants and animals. Contrary to popular opinion, most natural secondary metabolites are not healthy but very toxic. These compounds evolved over millions of years to be as deadly as possible to any potential attacker. The CC triple bond can impart enhanced metabolic stability and thus improve the pharmacokinetic properties of a given toxin, such as oral availability, plasma half-life, or tissue penetration. Alkynes can react irreversibly with nucleophiles and may therefore also act as enzyme inhibitors or as mutagens. Carbon-carbon triple bonds can therefore also be useful structural elements of drugs. This here is a small selection of drugs with alkyne substructures. Acetylene is the commercially most relevant alkyne. One industrial route to acetylene is the pyrolysis of methane with an electric arc. As a byproduct, hydrogen is formed. Careful pyrolysis of methane in the presence of oxygen can also give high yields of acetylene, and this is today its most common manufacturing procedure. Before the large-scale availability of crude oil and methane, acetylene was prepared by hydrolysis of calcium carbide, which was obtained from lime and coal. The main synthetic uses of acetylene include the addition of nucleophiles, for instance for the preparation of vinyl chloride, acetaldehyde, vinyl ethers and esters, and acrylic acid by addition of carbon monoxide. Base-catalyzed addition to formaldehyde yields butenediol, a valuable intermediate for the preparation of various solvents. The addition product to acetone can be converted into isoprene, an important monomer for the manufacture of polymers. Acetylene is also used for welding and cutting metals, because acetylene oxygen flames can reach up to 3100 degrees Celsius, a higher temperature than that attainable by burning propane or methane. Pure acetylene is unstable and can explode upon compression or heating, even without oxygen. Mostly hydrogen and carbon are formed during such explosions. The explosion limits of air-acetylene mixtures are much broader than those of ethane or methane, and such explosions are exceedingly violent. Okay, let's now have a look at the preparation of alkynes by dehydrohalogenation. Upon treatment with bases, terminal vinyl halides can undergo beta or alpha elimination, and both mechanisms have similar activation barriers. Alpha elimination yields a vinylidene as intermediate, which may rearrange to an alkyne or react by insertion or cycloaddition. I'll show you some examples later. The rate of halide elimination from vinyl halides depends on the precise structure of the starting material. Often, beta elimination from saturated aliphatic halides is faster than that of similar vinyl halides, as in the case of isopropyl chloride and 2-chloropropene. But this is not always so. Dichlorosuccinate eliminates HCl at about the same rate as chlorofumarate. And the elimination of hydrogen bromide from cis-bromostyrene is between 100 and 1000 times faster than the formation of styrene from phenetyl bromide. Arynes, by the way, are generally formed more slowly by beta elimination than non-cyclic alkynes. Vinyl halides with a trans hydrogen atom in position 2 undergo elimination easily and often much faster than those with only a cis hydrogen atom in position 2, as shown here. The reason is that the trans CH bond is closest to the empty carbon-chlorine antibonding sigma orbital. Thus, the shift of electrons from the trans CH bond into the antibonding carbon-chlorine orbital, as indicated by the green arrow, is easier than from a cis CH bond. The increased reactivity of cis isomers could also be due to better steric or electrostatic accessibility of the trans hydrogen atom, or to a higher ground state energy of the cis isomer. But cis vinyl halides are not always more energy-rich than trans isomers. In the case of 1,2-dichloroethylene, for instance, the cis isomer is more stable, due to hyperconjugation. I'll show you now some specific examples of alkyne preparations by dehydrohalogenation. Here, propanyl alcohol was obtained in high yield by heating trichloropropane first with aqueous sodium carbonate and then with potassium hydroxide. High temperatures generally favor eliminations at the expense of substitutions. In this example, chloromethyl THF was transformed into pentanol by treatment with an excess of butyllithium at 0 degrees Celsius. Even unsubstituted THF can be cleaved by organolithium or magnesium compounds upon warming, what is one reason why reactions with polar organometallics are usually conducted at low temperature. Here, an ethynyl ether was prepared by eliminating HCl and ethanol from chloroacetaldehyde diethyl acetal. Sodium amide was the base and the reaction already proceeded at low temperature. Most bases can also act as nucleophiles and reducing agents. Because of the high acidity of terminal alkynes, halogenated terminal alkynes are electrophilic halogenating agents and are therefore reductively dehalogenated by some bases. In this example, an excess of methyl lithium brought about two reductions. First, a reductive elimination of tosylate and chloride, and then the reductive dechlorination of a chlorinated alkyne. The starting material was prepared by addition of chloroform to an aldehyde. Also here, butyllithium acted both as a base and then as reducing agent. A better yield may have been achieved with a slight excess of butyllithium, not just the required two equivalents. This is an example of two-step dehydration of a methyl ketone to a terminal alkyne. Formulation with a Wiltzmeier reagent first yielded a chlorinated acrolein. Treatment with sodium hydroxide then caused deformylation and dehydrochlorination. I'll show you later some other strategies for the dehydration of ketones. Aliphatic 1,2-dibromides can be converted into alkynes by treatment with an excess of DBU, as shown here. Because propargylic ethers can isomerize to allenes, treatment with base should be kept as short as possible. In this instance, the primary bromide was eliminated first, and the initial elimination product was formed cleanly when the reaction was run with a smaller excess of DBU for only 1.5 hours at 60 degrees Celsius. Because of the high acidity of terminal alkynes, propiolic acids readily decarboxylate. Here, heating a dibrominated dihydrocinamic acid with potassium carbonate in DMSO gave a good yield of aryl acetylene by twofold dehydrobromination and decarboxylation. I've sketched here some of the possible reaction pathways. 3-halopropionic acids also decarboxylate readily by the mechanism shown at the bottom of this sketch. Thus, it is not clear at which stage decarboxylation occurred in this case. Under milder conditions, it is sometimes possible to prepare propiolic acids by dehydrobromination, as in this example. The yield wasn't high, though. This is another example of twofold dehydrobromination of a vicinal dibromide. Interestingly, the yield depended on the starting diastereomer, and only the 3O isomer gave a high yield of alkyne. Because bimolecular eliminations proceed preferentially from a conformation with anti-periplanar hydrogen, 3O and erythro isomers yield different vinyl bromide intermediates. And as mentioned earlier, beta eliminations from vinyl halides with trans hydrogen, such as the intermediate formed here from the 3O isomer, are faster than from those with only cis hydrogen. Thus, alkyne formation from the erythro isomer was less favorable in this case. However, sometimes even vinyl bromides with only cis hydrogen undergo elimination readily. In this example, the starting alcohol was converted smoothly into an alkyne just by heating with potassium carbonate. The hydroxyl group must have played some role in this elimination, because without it, no elimination occurred, even after refluxing for 9 days. With bases of low reducing power, such as fluoride or hydroxide, it is sometimes possible to prepare halogenated terminal alkynes, as in this example. Here, the dehydrobromination was complete after only 1 hour at 60 degrees Celsius. Brominated alkynes are often easier to prepare by bromination of terminal alkynes, for instance with bromine in aqueous sodium hydroxide. In this case, though, bromination of the olefin may also occur. Sulfide is not only a base, but also a strong nucleophile and reducing agent. In this case, both a dehydrobromination and reduction of a dibromovinyl group occurred. Only the required amount of sulfide was used to prevent displacement of the reactive chloride in position 2 of the quinoline ring. Also dBu can reduce brominated alkynes. Here elimination and reduction proceeded at room temperature in acetonitrile. By the way, vinylidene dihalides, such as the starting material here, can be prepared from aldehydes, ketones or lactones by treatment with carbon tetrahalides and phosphides or phosphines. In this example, an excess of LDA was used as base, but again reduction occurred, despite the low temperature. The large excess of LDA did not bring about arine formation in this instance. 1,2-dihaloethylenes can be converted into alkynes by halogen metal exchange with zinc, magnesium or polar organometallics. In the example shown here, zinc in THF was used, but the debromination was slow. When geminal dihaloethylenes are metallated, alpha elimination might occur and yield a vinylidene. This intermediate can rearrange to an alkyne either by migration of hydrogen or other groups. In the Fritsch-Buttenberg rearrangement, an alkyl or aryl group migrates, as in this example. Other groups than halides may also serve as leaving groups. Here a chlorinated sulfoxide rearranged in high yield to an internal alkyne upon metallation with a Grignard reagent. This here is another strategy to dehydrate ketones. An enol phosphate was first generated by phosphorylation of a lithium enolate and then converted into the alkyne with an excess of LDA. No isolation of the enol phosphate was required. Another strategy is the intermediate generation of vinyl sulfonates, as in this example. Vinyl sulfonates can also be prepared by oxidation of alcohols with an excess of sulfonyl fluoride in DMSO, as shown here. Best results in this specific case were obtained by a sequential treatment of the vinyl sulfonate, first with dBu and then with cesium fluoride. In this example, elimination of triflic acid from a vinyl triflate occurred upon palladium-catalyzed saponification and decarboxylation of an allyl ester. Another reagent suitable for the activation and complete dehydration of ketones is the 2-chlorooxazolium salt shown here. In this case, no strong base was required, just an excess of triethylamine. Even magnesium enolates can undergo elimination when heated with a Grignard reagent, as in this example. This dehydration strategy is of course only suitable for ketones that do not form a carbon-carbon bond with a Grignard reagent, such as highly enolized or sterically inaccessible ketones. Ketones are at the same oxidation stage as alkynes, and simple addition of water to an alkyne will again yield a ketone. 1,2-diketones therefore require a reducing agent to be converted into alkynes. Such a reductive deoxygenation can for instance be achieved by strong heating with phosphides, as in this example. I've sketched here the most likely mechanism. The driving force of such reactions is the formation of strong phosphorus-oxygen bonds and the ability of phosphorus 3 compounds to attack carbonyl groups nucleophilically at oxygen. Still another way to dehydrate ketones is by intermediate formation of sulfonyl hydrazones followed by their conversion into vinyl sulfones. Treatment of the latter with potassium terzbutoxide can yield alkynes, as in this example. The formation of vinyl sulfones from sulfonyl hydrazones is only rarely seen. I've sketched here one possible mechanism, but I dislike the formation of diamide, which is a strong reducing agent and usually hydrogenates CC double bonds, even at high temperature or in the presence of copper salts. Maybe the vinyl sulfones are sterically inaccessible to diamide, I don't know. The reaction only worked well under argon atmosphere, but not at the air. Tosyl hydrazones prepared from alpha-hydroxy or alpha-haloketones have again the correct oxidation state and can be converted into alkynes directly, without any reduction or oxidation. In this example, the hydroxy group was activated with carbonyl diimidazole. Heating to 100 degrees Celsius for 36 hours gave a fair yield of cyclic alkyne. Such reactions yield nitrogen and a sulfinate as byproducts, as shown here. Alternatively, heating sulfonyl hydrazones with a non-oxidizable base and an electrophilic chlorinating reagent can also bring about the formation of alkynes. In this example, hydrazone formation, chlorination and elimination were conducted in one flask, without isolation of any intermediate. Closely related to the previous example is the acid-catalyzed decomposition of alpha-hydroxy diazoalkanes. The scope of this reaction was narrow, and a number of byproducts were also formed. Another approach to alkynes is the oxidation of 1,2-bis-hydrazones. Again, these starting materials are not as readily available as vinyl halides or ketones, but occasionally can give convenient access to certain alkynes. In this case, the oxidation was performed with pure oxygen in dichloromethane and gave an excellent yield. Also, the oxidation of isoxazolones can yield alkynes, as shown here. Isoxazolones can be prepared from beta-ketoesters and hydroxylamine. Similarly, pyrazolones can be chlorinated and then cleaved at low temperature with sodium hydroxide. Substituted propiolic acids can be prepared this way. Condensation of aldehydes with some types of carbon nucleophile can yield suitable intermediates for the preparation of alkynes by beta elimination. In this recent example, a benzylic chloride was condensed with benzaldehyde with the aid of catalytic amounts of a sulfoxide. This sulfoxide acted as a source of the potassium salt of phenylsulfanic acid, which converted the benzylic chloride into a sulfoxide. Condensation and elimination regenerated the sulfinate along with a diaryl alkyne. Benzylic triazoles react in the same way as benzylic sulfoxides. Again, a large excess of strong base was required to bring about both the condensation and the elimination. Because aliphatic alkynes readily isomerize in the presence of strong bases, and because of the self-condensation of aliphatic aldehydes, this strategy was again limited to the synthesis of diaryl alkynes. Diazoalkenes, like the intermediate of this example, are unstable and easily fragment into nitrogen and a vinylidene. As mentioned earlier, vinylidenes can also be generated by alpha elimination of hydrogen halides from terminal vinyl halides. These vinylidenes may then rearrange to alkynes or undergo insertion or cycloaddition reactions. In this example, the intermediate diazoalkene was prepared by condensation of a diazophosphonate with an aldehyde containing a keto group. In this instance, one of the two vinylidenes rearranged to an alkyne, while the other one underwent insertion with the solvent. This here is a more convenient variant of this reaction, which bypasses the isolation of the diazophosphonate. The diazophosphonate was generated in situ by diazo group transfer with tosyl acide and nucleophilic deacetylation with potassium carbonate. Condensation with aldehydes then yielded the expected alkynes. Still another method to prepare symmetric diaryl alkynes is the dimerization of benzotribromides. Unfortunately, a large excess of copper was required and a lot of waste was generated. There are certainly more convenient methods to prepare this type of product, for instance the arylation of acetylene or of synthetic equivalents of acetylene, like 2-methylbutanol. Let's check some side reactions. One potential problem is the addition of nucleophiles to the alkyne, and strong bases are often good nucleophiles. Here, for instance, instead of dichloroacetylene, mostly a vinyl ether resulted. This can be avoided by higher reaction temperatures or less nucleophilic bases, for instance sodium or potassium hydroxide. Carbene insertions or cycloadditions of vinylidenes can compete with rearrangement to the alkyne. Here, for instance, a large amount of an enol ether was formed by insertion into the solvent OH bond. This here is an example of intramolecular CH insertion of a vinylidene, which was faster than rearrangement to the alkyne. Here are some more references, which you can also find in the description of this video. Under the Community tab of my channel, you can also find a PDF version of this presentation. The next video of this playlist is about the preparation of alkynes by alkylation of terminal alkynes. This is a convenient strategy for assembling larger carbon frameworks, also because alkynes can be readily hydrogenated or converted into many other groups, for instance ketones or secondary alcohols. See you!